So, one sec, sorry. All right, so I would like to recap what we learned yesterday. So it was about expander hierarchy. Okay. So I have defined something that I call alpha phi expander hierarchy, and this is a hierarchy that we can obtain from what? Anybody? Okay. Right. Sorry? Yeah, exactly. So it is something that we can get by basically first given a graph, compute the alpha bodily linked phi expanded decomposition. So alpha phi decomposition, and you get U1, U2, U3, and then once you compute this, you contract. Like once you compute this, you contract and you get some graph. And then given this new graph, you compute the decomposition again, you contract. And that, maybe I go to the, right. Given a graph, compute the decomposition of a graph and call the contracted graph to be the new graph and repeatedly do this. So you start with a graph and keep contracting. And then just from this sequence of contraction, you can obtain the corresponding hierarchy, right? Basically, this sequence of contraction would correspond to some laminar family of a vertex set, right? Basically, in the beginning, you have every node as its own set, and when you compute the first decomposition, you get this set, and then when you compute the decomposition in the second level, you get this. It would correspond to this. So it's really like a laminar family of our vertex set. And from this, you can create a tree. Okay. Is it clear to you how to construct this tree? Yes or no? Yes?
How do we deal with the multi-edges?
So if there are two edges here, we just create two edges here. So there are two edges. Yeah, we just think of a graph. After contraction, you just think you have a multi-graph. So if there are two edges, you can think of this thing has capacity 2. Yeah. second. All right. And now, basically this tree is a thing that we call expanded hierarchy. Yeah. So, just to make sure that we are really on the same page, like what is the capacity of this edge? Like if this is node V, the capacity of this edge is what?
Degree of the vertex in G node.
Yeah, this is just the degree of V. Yeah, and then if what about this one? Then this edge where this corresponds to this. It's just the degree of this guy. But this guy would, like the degree of this guy is what? It's just a cut size of this thing. Yeah. So like basically the weight of each edge here would correspond to some cut size for some cut in the original graph. Yeah. Okay. All right. And we have shown that this tree is a flow specifier of original graph. This tree, T0, is a flow specifier of G with quality which is something like log over alpha to the h times 1 over phi. And this thing can be made can be set to be small. How do you do that? So first of all, alpha, you should think of alpha as just 1 over log m. But this can be made small. How would you set? How would you make it small?
2 power root log.
Right. So if you set phi to be 1 over root log, then h is gonna be basically like root of log n up to log factor, and then so this become something like 2 to the root log n up to log, which is small. Okay, good. So that's the expanded hierarchy. Is given any graph, you can find one single tree that represents that graph. And it's not just, so basically when you can find, there is a name for, we just call, when flow specifier is a tree, then it is called tree flow specifier. So we just call it tree flow specifier. In the literature, or when you talk to people, people also call this tree a Regge tree, a tree that is a flow specifier or cut specifier. And this is just because this tree is discovered by Harald Regge in some not quite, when is it again? Something like this year, yeah. So it's not very old concept actually. Yeah. So what we just saw is that like this expanded hierarchy, which is conceptually very simple, right? You compute like a Bartley link, expanded decomposition, contract, and keep doing this. Then you can get a tree-flow specifier. I want to tell you a bit about the state of the art of tree-flow specifier, because this is such a strong concept, right? Given any graph, you can represent it as a tree. Who would have think that is possible? Like a tree is so simple, a graph is arbitrary, but you can represent a graph by one tree. So the state of the art is that if you want slow algorithm, they access a tree-flow specifier with this quality, like cut specifier with this quality. And for flow specifier, which is a bit stronger, you can get this quality. And if you just want not polynomial algorithm, but exponential time algorithm, one can get this quality. So it's better than what we saw in class, but it's slow. And actually, it's still open that is it possible to get log n? No one knows. Yeah. There is a low bound of log n, but upper bound we don't know. Yeah. Now, for fast algorithm, actually, it's possible to get log to the fourth. I think there is a way to improve it to log to the cube, but yeah, we can talk if you want to know. But the best thing in the literature is log to the fourth. And what we saw today, like last time, like in class, is this much. And actually, it is really the simplest construction known. Like all other previous works, it's much more complicated, like how to get it. So, I mean, this is simple enough to teach. Other is not. So, I would like to really know, like, is there any simple enough to teach tree-flow specifier with polylog qualities? That would be nice to know. Okay. Just want to like make some point about this. Basically, this is like tree is just something that we want, like that we like, because it's just so simple structurally and computationally. Like basically, think of top tree that we mentioned in class. I said that top tree. Once you have a tree, whatever you want to compute, you can do it, usually fast. And for top tree, it says that whatever you want to compute, you can even maintain it in the dynamic setting. So like tree is just very nice. And so it's like always it's like one of the main theme in graph algorithm in general, that when you have a graph, can we get some nice tree that represent it in some sense. You want a tree that preserve the graph in some way. And for example, you all know like a spanning forest preserve connectivity, shortest path tree preserve distance from the source. So like there is some tree that is more surprising, called Gomery-Hu tree. Have you heard of this thing? I want to tell you, it's quite nice to know. So this is a tree such that it preserves pairwise min cut. Exactly. So what do you mean? Like, can you? Do you all know about it or not? Like, if anyone don't know, I'll just tell you what it is. No? Okay, good. So it's a cool tree to know. Surprising that it exists too. Like it says that if you have a graph on here, actually there is another tree on the same vertex set, but different edge set. It's a tree. Okay. And now this tree will have weight on it. Okay. Like some number. Yeah. And now it turns out that for all S and T in V, min cut of G between S and T is the same as min cut in T from S and T for all pairs. So and not just, so it means what? If you have S and T here, and you want to compute min cut between S and T, given this tree, it's enough to just compute min cut between S and T in this graph. And actually, if you want to compute min cut between 2 points in a tree, that's very easy. Why is that?
Just go through the path and see the edge which is.
Exactly. Like just find an edge with the minimum weight in a path and return that. So that is a cut. That is a cut. And you can actually, like, for example, if you build a top tree on top of this tree, top tree data structure on top of this Gomori-Ho tree, you can query this thing in log n time. So you don't even need to go through the path. You can query it in log n time. So it preserves. So this is the case for every pair. Like you have this tree, pre-process this tree a bit. You can query every pair very fast. Okay. And actually, not just that. The cut here, the cut in this tree will be actually the same cut. Like it doesn't just preserve the value, it preserves the set itself too. Yeah. So very, very strong. So and conceptually there is something important about this. That is, you see pairwise min cut, there are like n square many numbers like because there are n square pairs. But if you see that this tree exists, it means that there are just n-1 possible number, and you can actually succinctly represent this n square number by just a tree. So, yeah. Right. So, that's surprising, and actually it was known how to compute this one. One can compute it in like it was shown like by Gomori and Hu themselves that you can compute it in Maxflow calls. And just last week, my co-author and I showed that actually Polylog is enough. So this is super recent. Okay, but like if I need to rate, like give like review like exciting score to each of these three, like maybe this is like 1. This is maybe like 2 maybe. This is like maybe 8. Yeah. right? And like there are other trees, so that people try to come up with, and it's useful in different settings. And you see like tree flow specifier. If it is a flow specifier, it's a cut specifier too. And this is just super strong that I wouldn't believe that it exists, but it does. Because this Kumari preserve just n square number, but flow specifier preserve like exponential information, because every cut is preserved, but there you need to pay some factor like a log factor. So, but yeah, it exists. Okay. Log n is a lower bound. Yeah. Yes. Yes. This is a score of this. Yeah. Maybe. Yeah. Is log n possible because this is known? Okay. And if you want to know how to get like a n log n, you can look at this paper. I put the link already there. Okay, so next week we're gonna basically use this expanded hierarchy to get approximate max flow in near-linear time, in almost linear time. Yeah. But okay, let's look at some exercise that I didn't prove in class, and maybe it's useful to show it. Is there some maybe this one. Maybe this one is good. Why is it not? Okay. This is why is it easy to get the tree flow specifier with bad quality, like with M quality? Let's see. Yeah. Okay. So maybe let's say that the graph is connected, and then and if I compute, let's say that the graph is connected and unit capacity, then I claim that any spanning tree is a tree flow specifier of this graph. Actually, it might be easier to think about cut in this case. it might be easier to think about, to say that this spanning tree is a cut specifier of a graph. And the reason is quite simple, right? Because, well, for all A and B, in the graph, mean cut of A and B, well, it's always between M and 1. And but mean cut between A and B in T is also between M and 1, between N actually and 1. So they must be within like M factor. So if you want it to be like B defined, so that is what we actually want in the definition is that mean cut of G is less than mean cut in T less than M. What you need to do here, you just need to put the weight of everyone here by M, right? So just put the weight M here, then you're done. Okay. And what if a graph is capacitated? Why is it the case that maximum spanning tree would work? So I will give you a hint. That is, the property of maximum spanning tree is this. That is, if T is a maximum spanning tree, max spanning tree, then given any cut S bar, then you know that if you look at an edge with maximum weight, so it's always going to be in a tree, right? Because it's maximum 1, yeah, it's maximum spanning tree. So edge max is always in the tree. There might be more than one edge crossing this cut, like because the tree might look like this, but the guy that has maximum weight along the cut will be in a tree for sure. So what does it mean here? It means that actually if you say that you look at any AB, and the mean cut might correspond to the mean cut between A and B will correspond to some cut. But you know that the maximum edge here will be in the tree, in the maximum spanning tree. So the cut size, so the cut size, if you count only one edge here, or you count all the edges here, it's just within M factor. Yeah. And now if you, so just from this observation, you can conclude, by scaling the tree a bit, you can show that maximum spanning tree will be like a cut specifier with quality M.
So we should multiply M into...
Yes. All right. That's exercise 2 exercise. Why is it the case that flow specifier is a cut specifier? And cut specifier is also a flow specifier with quality loss of log n. Okay.
Flow embedding implies cut embedding.
Yeah. So
Cut embedding implies flow embedding with congestion log n.
right. But like that thing is about like that's the right idea for sure. Yeah, it's just so what you say is that if H is less than G in cut sense, then H is less than G in the flow sense with maybe log n. And vice versa, and here you don't have any loss. So that's the right idea, except that it is not, you cannot use it as a black box, right? Because they don't even have like the concept of flow specifier here. We don't even need that the two graphs have the same vertex set. It really just preserves things about the terminal set. Yeah. But this is a case like if H and G were to have the same vertex set, then you can really just plug in this thing. Yeah. Okay. All right. So how to prove this? It's true, but it's not on the top of my head too. Let's see. So let's try to do this online, like a lot together. Yeah. So. So let's prove this case. If it is a flow specifier, then it's a. If it is a flow specifier, then it's a cut specifier.
Can you see the definition of flow specifier?
Here is a definition of flow specifier. Basically, you want H to contain the vertex set, like the terminal set, and given any demand between the terminal, if the demand is routable in G, then it should be routable in H. And if it's routable in H, it should be routable in G with some congestion. So, okay. So let me suppose that H is a flow specifier of G with for terminal set okay. And now we just want to prove that it is a cut specifier, which means that for all A and B in S, we want to say that mean cut in H AB is at least mean cut AB FG. Okay, so there are just two directions we need to do, right? Okay, so so let's just fix some A and B, and okay, fix A and B, and then any idea? So let's see. You have that. I mean, the idea should be like you will need to define some demand, and we know that some demand such that it is routable in H, and then because it is a flow specifier, this demand which is routable in H need to be routable in G too, and the fact that it is routable in G, it means that the cut in G is no. Let's see. Sorry.
So is that here D is can be function?
So D can be any demand on S.
Yeah, so then we can really choose just the edges between A and B.
Mm-hmm. Yeah. Like the demand that makes sense to me would be like the cross product demand between A and B. It's just a natural one. Like a cross product such that the sum of this.
We just set D equal to H.
D equals to H. Well, H may contain some other edges outside H too, outside the terminal. Okay, let's think about this offline because
Can't we just pick some S in A and D in B and then select the max floors?
say again. Sorry.
Can't we like pick some vertex in A, some terminal in A, some terminal in B, and like set it to be like that S D like max floors?
Yeah. Right. One sec. So. Yeah. Actually, what if we just said like maybe the demand can be as simple as two nodes, you mean? Like just say that pick S in A, pick T in T in B, and set the demand such that you want to route it as big as the max flow between like right.
But then the min cut may not have A and B.
Yeah, yeah. The min cut might be this. Okay. I think this is a good homework for everyone, including me. Okay. All right. Let's see, is there some other interesting exercise? Actually, is there some concept in class that you feel like you would like to get some revision? Like, that is not super clear. Anything at all? How is it going with the homework? I see. So I kind of skip this part in class, how to compute Buttery link expanded decomposition, and we can do that too. Yeah. So just to recall, here we want that given a graph, we want to partition such that each part is alpha phi linked, and the number of edges crossing is this much, like the number of Buttery plus phi volume log m. And the way to make this work in a convenient way, it turns out, is that is to look at this graph where you look at the induced subgraph with a k Buttery self loop. This is something that I have defined, right? So you have you start with the induced subgraph, and then for every Buttery edge here, what you do is that you create k many self loop in this. You will create k self loop. And for intuition, actually, if you think about this, if you just say that you add one self loop for every boundary edge, then you add one self loop. Then this graph is super similar to this graph, where you add one boundary edge. What do I mean by similar? So, first of all, the degree of every node inside you is the same, right? Because instead of having boundary edge, you just add a self loop. Yeah. So, and just because of this, like the structure of a graph doesn't really change. Like, so if you have a cut, so basically the conductance and everything is just the same, almost within some factor, like small constant factor. Yeah. So this is not very important, but the way sometimes I think of this graph, the graph with boundary edge, as this graph, like where the boundary edge is just a self loop.
So does the degree of self-loop is 2 or?
Oh, it's 1. Yeah. Like the degree of a node. Usually I think of it as just the number of edge incident to it. Yeah. So each self-loop is just one edge contribute to the degree. Yeah. But so when you look at this and you look at the degree, and if k is more than 1, then it just means that you kind of put more importance to the boundary than usual. Like if it's 1, then if it is 0, if it's just like a induced subgraph, you forget about boundary. If it's 1, it's really just like the graph with the boundary. If it's more than 1, you make it more important. And we basically can show that if you put like this much weight on each boundary edge. Look at this graph, and this is a phi expander, then you will be alpha phi linked. Okay. So the proof is simple, and I will just skip this. And now,
Actually, can I once recall the alpha phi link definition?
Alpha phi link just mean that it just means that it is both alpha parallelly linked, and this thing is phi expander. So it's like both good things happen at the same time. And now to prove that, like now what we want to prove is that given any graph,